And when things get complex, I have worked with Amar last 5 years or so. He makes things simple, right? So Amar is going to talk about using GPU-based edge clouds for ORAN to cut cost and save the power. So Amar, you are there?
Yes, I'm here. Yes.
Here at Aarna Networks, an open source software company creating platform for orchestration, among other things. Before that, he led the NFB business unit in Mirantis, and before that, he had other interesting leadership positions at various companies like Amulex, Philips, and HP. He's also author of ONAP Demystified book, holds a master's EE from University of California, Berkeley. With that, Amar, please take it over. I know you also have a time constraint, so please stop whenever you're ready to stop. I think this is an important piece of the topic.
Yes. Thank you, Ashutosh, for that introduction. Let me share my screen.
Yeah, you can share the screen.
Okay, so hopefully everybody, it's still coming. Everybody can see my screen?
Yeah, sure.
So I really found Arpit's presentation fascinating. And I also found it quite relevant because we happen to be a major contributor in the SMO, Service Management and Orchestration portion of the ORAN software community, ORAN SC. And in a sense, you can say we have like a commercial version. But anyway, that's not the topic for today. The topic for today is how can we use GPU-based edge clouds for ORAN? And in doing so, how do we cut costs, save power, and generate revenue? So if it sounds too good to be true, well, I'll show you how. So first we'll talk about the problem statement. Then we'll talk about how a GPU-based edge cloud solution can help, benefits of the solution, and a very quick demo, time permitting. So the first thing is up to 60% of the 5G cost is in the RAM. So the source is NVIDIA. So if you look at just overall 5G deployment, there's no secret, right? Most of the cost is in the RAM. According to a source from Ericsson, RAN sites account for 85% of the network consumption. It didn't directly correlate it to power, but I'm using that as a surrogate for power. So most of the power for the mobile network is also consumed by RAN. Tragically, the RAN is utilized only 30% at the maximum, somewhere between 20 to 30%, I think, according to the sources NVIDIA. So you have something that's costing you the most, consuming most of your power, but utilized at a paltry number of 30%. It's a huge waste of CapEx and power. So this is the problem statement, and this directly affects the CapEx for 5G rollouts. It impacts the speed, the velocity of 5G rollouts, because MNOs, can only absorb so much CapEx any given year. So this is just, not a great situation. So what if we could increase the utilization number? So that's where RAN in the cloud solution comes in. So this was shown at the last NVIDIA GTC. GTC is NVIDIA's annual conference. And the idea is that you run the DU and CU on a GPU accelerated cloud. So in the last Arpit's session, somebody talked about acceleration. So you have many ways to accelerate that. You can use a DPU, you can use a FPGA, you can use a GPU. So we are talking about the GPU-based acceleration. So you run DU-CU on that. But now when you have periods of underutilization, you can replace DU-CU with other workloads. So that's what this diagram is showing. So it's showing that during peak hours, we are running 5G only. So let's say you have two nodes, right? In this case, we are showing two nodes. One node is running DU-CU, the other node is running DU-CU as well. Now, Evening comes along, night comes along, and the traffic drops, utilization drops. Now what we can do is we can move DU2 to the first node. And so now we have both the DUs on that node shared across one CU. And the second node is now completely freed up. So we use it for an AI application, AI edge application. So that's the general idea of this scheme. And what are the attributes of a RAN in the cloud? So first of all, we have general purpose compute. So industry standard compute with a cloud layer such as Kubernetes. Then we use general purpose acceleration. In this case, we are saying a GPU that can be used for ORAN and non-ORAN workloads. So non-ORAN workloads would be things like AI ML, and that's kind of the top one, computer vision, Gen AI. But it could also be non-AI ML. It could be video services, it could be CDNs, it could be edge IoT, and more. The front haul, back haul would be software defined. Networking is software defined. So you can do the types of adaptive movement of workloads that I just described. And this is where you need ORAN. So for this scheme to work, you need a disaggregated RAN and you need a vendor neutral SMO, because the vendor neutral SMO now has to perform dynamic switching between the RAN workload, the CUDU, and something else like machine learning. So typically vendor SMOs are optimized for their own RAN. So they're not going to do something like this. So this is a huge way to, not only is it a way to cut CapEx and power, it's also a great way to sort of create demand for ORAN. So those are kind of the high level attributes of RAN in the cloud. Now, the benefits of RAN in the cloud are we can reallocate compute dynamically across the end-to-end stack as the need changes throughout the day. So the example I gave, during the daytime, you have heavy traffic and you run, all your nodes are running DUCU. The diagram only showed two, but I mean, you imagine many. Imagine there are many nodes. So all of them are running DUCU. And then you dynamically swap out DUCU and replace it with other workloads as needed. And what that does is it increases the effective utilization of the RAN hardware, because now you're using it not just for RAN, but for something else. So the RAN CapEx now effectively just went down because let's say 50% of the compute is used for machine learning, 50% for RAN, then your CapEx just got slashed by major amounts. Of course, I do acknowledge that this assumes that there are other workloads readily available. So the assumption is that an MNO can find some other workloads to run. If that's not, if that assumption is false, then obviously this scheme doesn't work. You're also sharing the power. So the power envelope that previously was assigned only to RAN is now distributed across multiple workloads. So the effective utilization, the RAN consumption, power consumption also goes down. And maybe the last one is the most exciting. RAN is a cost center, right? The RAN doesn't generate revenue per se. And indirectly it does because it's part of the 5G network and the 5G network generates revenue, but more or less the RAN could be viewed as a cost center. What if you could convert the RAN site into a revenue generating center through mechanisms like Gen AI? So if you could take the unused cycles, utilize them for something like Gen AI as an MNO, now you can monetize that. You can sell that to businesses, enterprises, and generate revenue. So 3 benefits, right? You cut the effective CapEx, you cut the effective power consumption, and you have the possibility of generating additional revenue. So you might be saying, this sounds great, but is there any proof that something like this would work? And yes, there is proof. So end of May, NVIDIA and SoftBank announced a major collaboration exactly around the scheme that I mentioned, that those AI factories or AI clouds or whatever you want to call them at the edge would be used for 5G and for Gen AI. So Gen AI would effectively generate revenue during periods of underutilization. Otherwise, you're running your CUDM. So with that, I would like to give a short demo. And let me share again to make sure that I shared with audio on.
You haven't started the audio yet, right?
No, so now I'm going to start with audio. So I'll just play it. It's 3 minutes. I hope you enjoy it.
Go ahead, please.
A traditional cellular network is made up of base stations, each of which covers a small area. Every base station needs dedicated cooling, backup power, and backhaul transmitters, and is directly connected to radio frequency antennas. Today, Virtualized Radio Access Network, or vRAN, is beginning to replace these individual base stations. Architected more like a data center, it significantly reduces overall costs for network operators and improves efficiency by centralizing common functions of multiple base stations in one location. But even with this improved architecture, because cellular networks must be designed to meet peak traffic loads, their average utilization is generally between 25 and 50%. Moving RAN compute into the unified accelerated cloud brings all the benefits of cloud computing, including resource pooling and higher utilization. It also opens up new revenue opportunities, such as running jobs in off-peak hours to guide business decisions the next morning. NVIDIA's RAN in the Cloud solution delivers 5G RAN on a cloud infrastructure that also supports AI workloads. This will have significant CapEx and OpEx benefits for both public 5G networks and enterprise and private 5G. Here we see a typical 5G workload on NVIDIA Aerial, a software-defined, fully programmable, and GPU-accelerated 5G vRAN. NVIDIA RAN in the cloud uses GPUs to do the processing for Aerial 5G vRAN functions, as well as accelerate complex AI workloads. But the true game changer is that compute resources aren't fixed in function. They're not dedicated to vRAN or AI. They can be dynamically allocated with the end-to-end stack as needs change throughout the day. End-to-end orchestrator with closed-loop automation with RAN domain service management and orchestrator is part of NVIDIA RAN in the cloud stack. When 5G network demand peaks, compute resources are available, including inline L1 GPU acceleration for 5G physical layer processing and full stack framework support for G-Node B integration of L2 and L3, along with manageability and orchestration. But when 5G loads are lower, excess capacity can be directed towards AI computing, maximizing the utilization of available resources and leading to a lower total cost of ownership. Radisys and Aarna networks provide single pane of glass solutions, including 5G Layer 2 Plus and 5G Core, and Orchestrator to dynamically manage these applications and services from end to end in real time. To learn more about how NVIDIA Aerial can improve the efficiency and utilization of cloud-based 5G vRAN, visit the links in this video's description.
All right, so that was just a quick demo. As the demo already said, the CUDU came from Radisys. I would have to try and remember who the RU was. It was some RU vendor. The orchestrator SMO came from Aarna. And maybe I'll just talk a little bit about our open source approach. So as Arpit mentioned, ORAN SC is the open source community that is implementing various parts of the ORAN Alliance specification in the open source. And they have multiple groups, multiple projects. We are part of the SMO project. And I think SMO is one of the more mature projects in ORAN SC. So our SMO is a slight modification of the ORAN SC. And we are an active contributor on ORAN SC. We've contributed to the O1 interface. That's the main one we've been working on. Now we are working with Red Hat and others on the O2 interface as well in the open source community. So with that, I would like to end my presentation for today. If anybody has questions about this slide deck or about open source in general, how to get involved with ORAN SC, how to contribute, how to consume ORAN SC, and how to try it out in your own lab. I mean, it is open source, it's free to try out. Anybody can try it out. So if you're interested in any of these topics, please do contact me. So with that, Ashutosh, thank you.
Thank you. I know you had a time constraint. There are some questions in the chat. We will send it to you.
Yeah, maybe I can just take one and then the rest we can.
I guess you don't have time now to take any questions, do you?
I could take one and then maybe we'll pause.
Any question from the audience here? Otherwise, there is a question on the chat. Maybe you can answer that.
Yeah. Are you using AI/ML to dynamically or more static in nature optimize allocation for RAN resources or other acceleration? Are there SMO resources then in somewhat generic or RAN optimized? I would say it's dynamic because we are constantly monitoring the traffic profile. And then based on the traffic profile, we can swap out. So if you have, let's say, 20 nodes running DUCU, we can dynamically say, okay, all 20, or we now take 5 or 10 for CUDU and the rest. So it's completely dynamic. And is the SMO resource then somewhat generic or RAN? Well, the SMO is fully ORAN compliant, but in addition, it can also orchestrate edge computing applications. So that's the sort of the SMO plus here. And the resources, the RAN resources obviously are RAN optimized CUDU. And the others, like machine learning, they don't even know what RAN is. I mean, they're just completely generic edge computing applications. So I know it's been a long day for everyone as well. So Ashutosh, thank you. And any other questions, I'll be happy to
Amar, thank you.
answer by email.